Hi, everyone. Well, let's continue, okay? We just have one more big concept that I want to introduce, and that's the auxiliary field. I also want to clean up a minor error. Hold on one second. Okay, so we said a moment ago that a magnetic moment in a magnetic field will feel a torque that will make it want to line up with the magnetic field in some sense. And because of that, it has magnetic energy. However, I made a mistake. I said that U is m dot B. In fact, it's minus m dot B. Okay, I think I wrote the right answer, and then I thought I corrected myself, but I got mixed up. A magnetic dipole placed in an inhomogeneous field will feel a net force. And we can find the force as minus the gradient of the potential energy, which turns out to be plus the gradient of m dot B. Okay? We'll come back to that in a few moments. Very good. We introduced the magnetization and said that the magnetization, the net magnetic dipole moment, is just 1 over the volume of the sample times the sum, the vector sum of all the magnetic moments in the material. Okay? And finally, we're ready to introduce the auxiliary field H. Okay. So I'm just going to write equations that define it, first in a vacuum and then in a magnetic material. I think it'll make sense that way. In a vacuum, the H field is related to the B field in a very simple way. We can just write B is equal to mu naught times H. They're just proportional to each other, okay? In this equation, of course, B is just the magnetic field, right? But in fact, to be very precise, this is the called the magnetic induction. A term that we're never going to use again, okay? But in any event, it's measured in Tesla. H properly is called the magnetic field. Although in fact, everyone just calls it the H field, and that's what we're going to do from now on too. And it has units of amperes times meters, or Oersted. And finally, mu naught is a familiar constant. It's the permeability of the vacuum, 4 pi times 10 to the minus 7, and it clearly has units amp meters divided by Tesla. Okay? Now, if we only worked in the vacuum, there'd be no point to even consider H. What's interesting is the relationship between B and H in materials, magnetized materials. Then B is equal to mu naught times H plus M. Okay? So now we can kind of see how this works. Suppose I have an electromagnet that's, and then I place in the field of the electromagnet a piece of magnetic material, iron, I guess. Okay? The iron magnetizes. Well, the B field is due to the sum of the magnetic field produced by the magnet and the magnetic field produced by the magnetization. Whereas it turns out that the H field is just the field produced by the electromagnet itself. Okay? B and H play kind of similar roles to E and D, the displacement field, when we talk about dielectric material. We won't have to deal so much with H, but I want to introduce it to you because, well, it's a very familiar quantity. Okay? Now, B and H are particularly simple if we talk about what are called linear materials, or linear magnetic material. What's a linear magnetic material? It's a material where the magnetization is just proportional to the H field. Okay? So here we say M is equal to the magnetic susceptibility times H. Here things are a little bit different than they were in electrostatics. In electrostatics, it was D that was multiplied by the dielectric constant times the electric field. But here, it's the other way around. Okay? In any event, M is proportional to H in linear materials. And so in that case, B is equal to 1 plus magnetic susceptibility times mu naught times H, or, I'm sorry, 1 plus magnetic susceptibility, yes, excuse me, or this is just written as the permeability times H. Okay? So in linear magnetic materials, we can say that B is equal to the permeability of the material times H, where the permeability is simply mu naught times 1 plus the magnetic susceptibility. Okay? Couldn't be simpler. Very good. Well, that's really what I wanted to talk about. But I will mention one more thing, okay? I want to talk about the forces on magnetic materials, because when we play with magnets, that's the thing we see, the forces between the magnet and the magnetic material. So let's look at that. So imagine the following now. Suppose that we have a magnet. Oh my goodness, but not that magnet. Suppose we have a bar magnet, and the north pole of the bar magnet is here. We know that the north pole of a bar magnet is a source of magnetic field, and magnetic field lines diverge away from the North Pole and eventually wind around to the South Pole, but we don't care about that right now. And suppose that we place into the field of this bar magnet a piece of magnetic material that has some magnetic susceptibility, chi m. Okay? Let's see what the force on the magnetic material will look like. So the force is equal to, is given by the gradient, minus the gradient of the potential energy. Sorry. Which is equal to the plus the gradient of m dot b. But the net magnetic moment of the material is just its volume times its magnetization. And the magnetization in a linear material is just magnetic susceptibility times the permeability times H. That's the magnetization. And then we have to multiply by H again. Okay? So this works out to be the volume. Well, let me write it like this. Volume times the permeability times the volume. I'm sorry, the susceptibility times permeability times volume times the gradient of H dot H, which is just the magnitude of H squared. There we go. There's our result. So here's the idea. Suppose that we have a material with susceptibility chi m. And let's suppose chi m is a positive number. Then the force on the material will point in the direction of the gradient of the magnitude of the field squared. That means that the force will point towards the high field direction. It'll point towards the region where the magnetic fields are stronger. And so in this case, it means the force will be towards the magnet. And the material will be attracted to high field regions. In other words, what we found is that for a material where the magnetic susceptibility is positive, these materials will be attracted to strong magnets. On the other hand, if there were materials that had a negative susceptibility, they'd be repelled. Okay, we've certainly seen things attracted to strong fields. Remember this? What about repelled? Well, that's going to have to wait until next time. All right, so let's stop here.